Okay, in this video I'd like to talk to you about orbital motion, which is a type of circular motion, and it's caused by gravitational force. So it's going to be a combination of the last couple things that we've been talking about. I'd like to start with the question of how many people are in space right now, which is answered always by howmanypeopleareinspacerighttnow.com. You can see the International Space Station if you know when to look and where to look. You don't need a telescope or anything, and it moves pretty quickly. If you've never seen it, you might want to check out the app. This little video clip is not the best quality, but you can see something streaking across the bottom of the sky there just above the trees, going from the center of the screen to the left of the screen. That's what the International Space Station looks like. So if you check out the NASA website or the app, it'll tell you different times, usually around sunrise and sunset, when you can see the International Space Station going by in orbit. And the question we want to talk about right now is, why don't they fall down? If you were to take a look at one of the astronauts and draw a free body diagram, you would see the force of gravity pulling down on the astronaut, and that's it. Gravity definitely still exists up there. Sometimes people tell me the reason they don't come down is because there's no gravity. There's a lot of gravity. At the altitude that they are, which is about 400 kilometers above the surface of the Earth, the acceleration due to gravity is pretty close to 9.8 meters per second still. If you went straight up to that altitude and stopped, you would fall straight back down really quickly, again at almost 9.8 meters per second. So why don't they? That's what we're about to get into, and the answer really is the same reason that we don't see motion like what we're witnessing in this cartoon right now. Wile E. Coyote does not actually move like this. Your motion in the X direction and in the Y direction and in the Z direction do not depend on one another. He's not going to refrain from falling until after he stopped moving. He would actually move like we learned about with projectiles. The reason that the astronauts don't fall and hit us, even though gravity is pulling on them, is the exact same reason why you would not get hit by a cannonball if you were standing at the bottom of the cliff and the cannonball were fired out horizontally. If someone dropped it, yes, it would fall straight down and hit us. Much like I said that the astronauts would come right back down if they launched straight up and just stopped. But if they are launched out at a horizontal motion, then just like this cannonball, they would move sideways as they came down, and therefore they would not fall straight down and they would miss us. When we talked about projectiles, I showed this slide very briefly, and I mentioned that if a projectile is fired horizontally fast enough, and I was sort of vague about what fast enough means. If it's fired horizontally fast enough, then its curvature as it falls as a projectile would start to need to include the curvature of the Earth. And that's a pretty fast projectile. This is much faster than anything that you and I can throw or launch with everyday experiences. But for people who are launching things like artillery or NASA rockets, the curvature of the Earth definitely matters to what they're doing. This is an OpenStax image that is basically just a redrawing of something that Isaac Newton drew in his own notes and work when he was first working on the idea of things like universal gravitation. It occurred to him, this idea that if you were to fire a cannonball fast enough, then the curvature of the Earth would start to matter to the path of the cannonball, that by the time it fell down to ground level, it would have gone out so far that ground level itself had curved. And so he reasoned, he said this was not possible technologically, but he reasoned that at least theoretically, if you could get above the Earth's atmosphere so it didn't cause air resistance, you could fire a cannonball horizontally so fast that the arc of it falling would match the arc of the Earth's curvature. And this probably still sounds a little bit weird, and we have a slide coming up a little bit here that might explain it a little bit better. I also want to point out what OpenStax did not include is that if you go faster than the speed necessary to achieve a circular orbit, your cannonball would actually achieve an elliptical orbit. It would not orbit in a perfect circle, but rather as it orbited, it would move farther and farther away, and because it's moving farther and farther away, gravity would cause it to slow down. As it moved farther away, it would then, some of its kinetic energy would turn into gravitational potential energy, which would eventually turn back into kinetic energy as it comes back in. Although you can see there's a little mark on here called escape speed. Escape speed is how fast you would be going so that Earth's gravity would always be slowing you down, but would never actually win and pull you back. I do want to share with you a little bit about the scale of the distances we're talking about before we get into some of these calculations. This is a scale of how far away the moon is from the Earth. It's about 60 Earth radii, and it varies a little bit in its orbit. From one month to the next, the moon gets a little bit closer and a little bit farther away, but it's about 60 Earth radii away from the Earth on average. And we're going to get in much closer to the Earth to see the scale of how far away things are, like the International Space Station. This is to scale. If you look at this image of the Earth, how thick the atmosphere is on that, that's to scale. I remember working at a science museum in Richmond, Virginia, and I was told that there's a big globe out front. It's about 9 feet in diameter, and I was told that if you put your hand on that globe, the thickness of your hand signifies how thick the atmosphere is on the actual planet. So anytime you put your hand on a globe, the thickness of your hand is probably thicker than how thick the atmosphere is around our planet. It's a very thin layer, and that means to get above the atmosphere, you don't actually have to go up very far. The International Space Station is at about an altitude of 400 kilometers. So that's not that far away. It just is straight up. So what I'm saying by this is the astronauts are therefore very close to the planet still, very nearly at 9.8 meters per second of straight down acceleration. But the part we have to remember is they're moving in the direction of this arrow right here at, I don't know if you noticed this on the earlier slide, but I have the speed actually listed right there, somewhere between 6.9 and 7.8 kilometers per second. So they're moving extraordinarily fast to the side. There's still an aspect of this that probably seems a little bit strange, and what we need to consider is what the direction down means. The direction down changes for the perspective of an astronaut who's moving that fast as they're moving around the planet. Down, for example, on this drawing here is not to the bottom of the screen. As you move from point 1 to point 2 to point 3 to point 4, down is always directed toward the planet. So as they move from point 1 to point 2, the direction we would think of as down changes a little bit. And as they move from one side of the planet to the other side of the planet, they are constantly being pulled in toward the center of the planet. That's the important part to remember here for why they keep missing the planet as the planet keeps trying to pull them in. If they slow down from their orbital speed, they would definitely get pulled in and hit the planet. In fact, that's how they come back. When you want to come out of orbit, what they do is slow down, and gravity pulls them in. An important point that I mentioned earlier, and I want to make sure that I emphasize it again, is that means that you cannot get into orbit by launching straight up. Orbit is not a height. It's not some sort of track that you fall into. It is a matter of going fast enough, but also, as it says here, going parallel to the Earth's surface. If you just go straight up, then gravity will pull you back down. In order to achieve orbit, you have to launch. This is an image of a space shuttle launch. They go up, but then they also very quickly start turning themselves sideways. They have to be traveling across the ocean, parallel to the planet's surface. So an example question we would have would be something like, how fast is the International Space Station moving in order to stay in a circular orbit at the altitude that it currently is? I looked it up. It's currently at 418 kilometers above the Earth's surface. And I gave the answer earlier to how fast they're moving, so we'll know if we're doing it right. The way that we're going to do it is this. We're going to say we know Newton's second law is our starting point every single time that we're talking about why an object is moving, how it is moving. In fact, that's what this equation has, is on the left side why the object is moving, and on the right side how it's moving. The right side being the kinematics, the acceleration. That's our whole connection between dynamics and kinematics, is Newton's second law. What is the net force acting on the International Space Station? Gravity is the only force acting on it once it is above the atmosphere. It's not in contact with anything. There's no ropes pulling it or anything like that. It's just up there and gravity's pulling it down. So gravitational force is the net force on it, and its motion is circular because it's in orbit. So we know that that means the mass times the centripetal acceleration, so v squared over r, where r is the is the radius of the orbit. The force of gravity we know from universal gravitation is the capital G, universal gravitational constant, times the mass of the planet times the mass of the International Space Station, because those are the two things attracted to each other gravitationally in this problem, divided by the radius of the orbit squared. That equals the right side of the equation, which is the mass of the International Space Station times the speed of the orbit squared, the speed of the International Space Station squared, divided by the radius of the orbit. Of course, if you're looking at this, you're seeing there are certain terms that show up on both sides. For example, the mass of the International Space Station shows up on both sides, and it divides out. The radius of the orbit on the left side of this equation is the same value as the radius of the orbit on the right side of the equation, but it's squared on the left side. So I get to divide it out on the right, but I only get to divide out the squared on the left. They're both in the denominator, so they do divide out, but I'm still left with a radius of orbit on the left side here. I want to make a note about the radius of the orbit. The radius of the orbit is the altitude in addition to the radius of the Earth. That 418 kilometers of altitude is very small compared to the radius of the Earth. And we want to add them both on there to get the full radius of the orbit that the International Space Station is traveling, which is 6,789 kilometers. So that brings me to the point where I have the gravitational constant, which is given at the top of the page here, times the mass of the Earth, which is given at the top of the page here, divided by the radius of the orbit, which we just calculated, equals the orbital speed squared. So if I put my numbers in, and I'm careful with my squared at the end, I need to square root all the numbers to get a orbital speed or an orbital velocity, I come up with 7,660 meters per second is how fast they have to be moving sideways. That's a key component to this. If they move that fast up or down, they're not going to be in orbit. They have to be moving parallel to the planet surface in order for gravity to be perpendicular to their speed and put them in circular motion. That is, by the way, just over 17,000 miles per hour. That's how fast a rocket has to get up to launch a satellite or itself into a low Earth orbit. I'd like to do another example for a different type of satellite that is much farther away from the planet than the International Space Station is. There are a lot of satellites that are very close to the planet, that low Earth orbit, and then there are certain ones that are much farther away, including certain ones called geostationary or geosynchronous satellites. We'll talk about why anyone would want to do that in just a moment. But if you look at this image, what you'll see is the planet spinning, and we know that the planet orbits at a constant rate of 24 hours per day. A geostationary orbit means that you've put a satellite up that takes 24 hours to orbit the planet once, which means, as you can see on this image here from Flipping Physics, the satellite orbits the planet in a way that makes it seem like it's not changing where it is compared to the people on the planet. Someone who's out in the middle of the Pacific Ocean looking up at this satellite would see the satellite above them at all times. As you move, it moves at the same angular velocity. So the question is, how far out would you need to put a satellite in order for it to be in a stationary orbit compared to you as you move around on the planet just by virtue of the Earth rotating on its own axis? We'll start this problem by talking about the fact that the force of gravity is the force that is making this object move in a circular motion, and we've already established that that simplifies down to the gravitational constant of the universe times the mass of the Earth divided by the radius of the orbit equals the speed of the orbit squared, or the velocity of the orbit squared. I do want to point out that the radius of the orbit and the speed of the orbit are very different for this than they were for the previous problem. So in this case, what are we looking for exactly? We're looking for the radius of the orbit. We're trying to find out the altitude. So we need to first find the radius of the orbit, and then we'll subtract away the radius of the Earth from the radius of the orbit, leaving us with the altitude. So solving for r. Well, before I solve all the way for r, I'm just going to take the r and put it up on the right side here, and I'm going to have g times mass of the Earth equals the speed of the orbit squared times r orbit. And the reason I don't want to isolate it just yet is I know that the speed of the orbit in meters per second is a value that I'm not given. But I do know that the angular speed or rotational speed of the orbit is going to be the exact same as the angular speed or rotational speed of the Earth. And we know what the rotational speed of the Earth is. It is 2 pi radians, or 1 full rotation, every 24 hours. So 2 pi radians per day, and I need to have it in radians per second in order for the units to work in my calculations. So I need to find out how many seconds are in a day. I'm not going to show that here. We've done that before. It's going to allow us to say that the speed of the orbit, by the equation v equals r omega, the speed of the orbit is going to be equal to the radius of the orbit that we're trying to find times the angular speed of the orbit, which we already do have the ability to calculate. So substituting that back in, the gravitational constant of the universe times the mass of the Earth, those are two constants on the left side of our equation, will equal the quantity, radius of the orbit times omega of the orbit squared, times the radius of the orbit. That means radius of the orbit shows up 3 times here, and I get an r cubed out of this. So if I then divide both sides by omega of the orbit, the angular rotation value of the orbit squared, and this is where you're going to have to be really careful with the math. I actually made a mistake the first time I went through this, and I couldn't figure it out at first. It's because I forgot to square my omega. The radius of the orbit cubed, I move over to the left side here. Oh, and I misspelled orbit. Whatever. Equals capital G, which is the 6.67 times 10 to the minus 11th meters cubed per kilogram second, times the mass of the Earth, which is the 5.972 times 10 to the 24th kilograms, divided by the angular speed of the orbit, which is the same as the angular speed of the planet, which is 2 pi radians per day. And instead of day, I have the 86,400 seconds that one day is equal. And what I calculate from that is that the radius cubed is 7.53 times 10 to the 22nd meters cubed, which means if I cube root both sides, I get that the radius of the orbit is, oh, what is that? This is why we have scientific notation. 42,230,433 meters? That seems like a lot of meters. And it is. We would normally measure this in kilometers. It's about 42,000 kilometers. But that's the radius of the orbit, not the altitude. So if you look on the image here, you can see that the radius of the Earth and the altitude add together to give the radius of the orbit. That's right about where the satellite image is going right now, is through the radius of the Earth plus the altitude on the image. So I'm going to subtract out the radius of the Earth, and I'm therefore going to be left with the fact that the altitude is about 3.6 times 10 to the 7th meters, which is about 5.6 times bigger than the Earth's radius, meaning that this picture here isn't quite to scale. That's okay. 5.6 times out, or 5.6 times the radius more altitude. The reason that you would have a geosynchronous orbit or a geosynchronous satellite is actually really obvious in this image. This is a neighborhood in Richmond that I happened to be riding my bike through, and I noticed there's a lot of satellite dishes, and they're all pointed the exact same way, and it just made for a really interesting photograph to emphasize the reason that these dishes are all pointed the same way. They're pointed up into the sky at a satellite. And that doesn't help you if the satellite is moving like the International Space Station, which orbits the planet like every 90 minutes or so. And you saw in that earlier image, it's just racing through the sky. Your satellite dish isn't going to get a message from it consistently. However, these dishes get a very consistent message from the communications satellite that they're pointed at, because that satellite never moves from the perspective of these dishes, because it is in a geosynchronous orbit, meaning that it is following us in one orbit on our axis every single day, going around our axis once a day, just like we do. From space, it kind of would look like this if all the satellites were brighter. We have a whole bunch of little satellites in close to the planet's surface there. That's things like the International Space Station and a lot of other satellites that are in close. But then that ring that's around the Earth like that, that's all artificial satellites. and communication satellites mostly. And then all that other stuff out there. There's the GPS satellites and weather satellites and military satellites. There's all kinds of stuff out there. But the ring is what I wanted you to see here. That ring of geosynchronous satellites is out at that specific distance, that specific altitude from the planet that we just calculated. All right, that's it for this video, and there is still another example video coming up for circular motion.